Hi, welcome to my presentation on the Gatekeeper algorithm that we will be presenting in these few slides. The main challenge that we're trying to address is how can we safely operate a nonlinear system online in dynamic environments when there is limited perception. This is motivated by a classic aerial firefighting mission called the Firewatch mission, where this helicopter is tasked to figure out where the perimeter of the fire is without entering the fire as it's doing so. In this dynamic environment, it is difficult to use classical methods of safety critical controls because we have limited information about the environment and the environment is changing rapidly. Our solution is this algorithm called Gatekeeper, where the idea is to use the nominal trajectory generated by a nominal path planner and a backup controller, in this case, for instance, fly perpendicularly away from the fire, to be able to construct so-called committed trajectory and show that this committed trajectory is going to be safe for all future time. The main objectives of this presentation are to show you how this strategy renders safety, how do we implement this, i.e. the algorithm, and what the benefit is of doing this additional step. The key idea of Gatekeeper is that we add this step in between the perception, planning, and control modules of a robotic system, where the safety Gatekeeper takes a nominal trajectory generated by a path planner and converts it into this committed trajectory that is guaranteed to be safe. So let's take a look at what the key idea behind the algorithm is. The objective is to design a controller that guarantees that if you started within some safe set, you would remain within the safe set. However, we have only limited information about safety, and S of t is actually unknown a priori. So instead, what we do is we have this recursive guarantee of safety. What we'll do is we'll construct a candidate trajectory and check whether it is valid. What this means is we take this candidate trajectory defined for all time into the future, split it over a horizon tk to tk plus b, and then check whether over this horizon we stay safe and whether we reach a controlled invariant set. The idea here is that bk is the set that we perceive to be safe at any given time. And if we can check that while we traverse this trajectory, we are safe, and we reach a controlled invariant set, then that means that this particular candidate trajectory is a safe candidate trajectory to execute. Since it's valid, this candidate becomes the committed trajectory. We continue tracking this forever into the future. When new information comes in, we can update the candidate trajectory and repeat this process to follow the nominal trajectory as closely as possible. Let's take a look at how this looks in the algorithm. The algorithm takes the current state in the nominal trajectory and first constructs a candidate trajectory. We do this using a numerical ODE method. Essentially, what we do is we solve the dynamics of the system subject to first track the nominal controller for some time tk to tk plus ts, and then track a backup controller between tk plus ts to tk plus ts plus tb. And this is a finite horizon, a short finite horizon, over which modern ODE solvers are able to solve the trajectory extremely quickly. We get a candidate trajectory and check whether or not it's valid according to the statements before. If it is valid, it becomes the committed trajectory, and if not, we decrement the time and continue to solve for new candidate trajectories. And if we're unable to find a candidate trajectory that is valid, we exit by simply using the previous committed trajectory. Since the previous committed trajectory was guaranteed to be safe in the previous instance, we know that this new trajectory will continue to be safe. Now I'm going to refer you to the paper for the full proof and how we exactly implement this algorithm. And also to robustify against disturbances, we need to make a small modification to the isValid function. And for that, I also refer you to the paper, or please visit me at the poster session later. What does this earn us? So here we have a more complicated firefighting scenario where we have a non-convex safe set, and we have three different controllers: the nominal controller, the faster controller, which is a MPC-based method, the backup filters approach, which was proposed by Professor Aaron Ames' group, and the Gatekeeper method that we propose. What we see is that Gatekeeper stays very close to the boundary, but still renders safety and doesn't get trapped inside the pocket in the way that the backup filters or MPC methods can get trapped. We have very low computation time. We take about 3 milliseconds compared to about 80 milliseconds for an MPC type approach, and we can explicitly handle nonlinear dynamics. So to conclude, we started with this challenge of the Firewatch mission, or in general dynamic environments where you have limited information. We've constructed an algorithm to create candidate trajectories and therefore committed trajectories that are guaranteed to be safe for all time into the future. And we are currently working on onboard experiments where this quadrator is planning, perceiving, and filtering the trajectories online and is able to remain safe. All of the computation here is happening on board. We hope to release these results very soon. Thank you very much.